Bismillahirrahmanirrahim. Welcome to the lecture Message Authentication Code. Message authentication is concerned with protecting the integrity of a message, validating identity of originator, then non-repudiation of origin, dispute resolution. So, as far as the message authentication is concerned, when message is sent by the sender to the destination, there should be a verification mechanism to identify whether the data has been modified or not. So, such mechanism we can call it as integrity check. So, basically message authentication code can be used to verify the integrity of the message. In the previous chapter, hashing technique, we saw that how hashing technique can be used to verify the integrity of a message. Similarly, in this lecture we are going to see how message authentication code is used to verify the integrity of the message. So, in general, message authentication is concerned with protecting the integrity of a message to verify whether data has been modified or not. So, we can use hashing technique, or we can also use message authentication code. This is what we will discuss in this chapter. Then validating the identity of originator. So, source identification. To identify the source, whether the source is genuine or a fraudulent one. So, that can be that is also considered as a message authentication. So, when sender is sending the message to destination, the destination has to verify whether the message has come from the genuine source. Okay. So, that process is called validating identity of originator. So, that also can be considered as a form of authentication. Okay. So, now in this chapter we are going to discuss the technique of message authentication code, MAC. So, the MAC can be used to verify the integrity of a message, as well as it can be used to verify the identity of the source from where the message has been originated. Okay. So, now message authentication, how we can perform the message authentication? It can be performed using hash function, then encryption technique. Okay. So, in the chapter 1 we saw how hashing function can be used to verify the how hashing technique can be used to verify the message authentication. How it can be used to implement the message authentication. Similarly, in this chapter we are going to see how message authentication code technique can be used to implement the concept of message authentication. So, this image shows the general picture of the message authentication code technique. So, according to this technique, the message goes as an input to a MAC algorithm, which accepts the key and the message as the input and produces a MAC value or tag, we can call it, and authenticator. So, this authenticator is attached with the message and sent to the receiver. The receiver once again computes the MAC value from the message what it has received using the same symmetric key. So the sender and the receiver, they have to share the key, and after computing the MAC value once again by the receiver, compares the computed MAC value with the MAC value sent by the sender. If they are matching, it means that the message has come without any modification, has been transmitted without any modification. And also, not only it verifies the integrity of the message, also it verifies the source from where the message has originated. It authenticates the sender also. So two kind of authentication happening here: message authentication as well as the source authentication, sender authentication. Why? Because let us assume there is an adversary, there is an attacker or opponent. If the opponent is changing the message, for example, let's say the opponent is sending the message, changing the message, then in the receiver end, if the receiver computes the MAC value from the fraudulent message, then the receiver would get a different MAC value which would not match with the MAC value sent by the sender. Okay, so the adversary or the attacker cannot, it is difficult for the adversary to compute the exact MAC value unless or until the adversary has the key, okay, and the key is not shared with anyone except the sender and receiver. No other person knows the key. So the MAC basically is used to authenticate the message as well as the sender of the message. These are the some of the message security requirements. Let's discuss some of them. So disclosure. So disclosure actually talks about the confidentiality, privacy, release of message contents to any person or process not possessing the appropriate cryptographic keys. So basically the message, when it is transmitted or when it is in storage, only authorized person should be allowed to access the message. So the privacy of any data has to be preserved. The privacy of the message should not be compromised. So these are some of the security requirements of data or message, we can call it. So the message privacy has to be preserved. That is what discussed. The first requirement, insist, disclosure. Traffic analysis. So adversary or attacker can analyze the traffic when there is a message transmission takes place across a network. So that could help the adversary to discover some kind of pattern in the traffic between two parties. So basically the frequency and duration of connection. So it could reveal some kind of information pattern to the adversary which could help him to initiate some kind of attack. So that is called traffic analysis. So basically during the traffic analysis processes, the security systems should be in place, and that shouldn't allow the adversary to fetch more information when parties are sharing the information across the network. Then masquerade. So basically it talks about insertion of message into the network from the fraudulent source. So basically the some fraudulent source acts as a genuine source and fabricates a message and send the message to the receiver, acting like a genuine source. Content modification. So the content of the message, such as insertion, content of the message is modified while it is transmitted. What kind of modification means? Insertion, deletion, etc. Sequence modification. So when communication takes place between two parties, when the messages are sent from one party to another, the message sequence can be altered, like inserting a message or deleting a message in the middle or reordering the message. So that we call as sequence modification. And also timing modification means like delay or replay of message in a connection oriented application. So replay attack, we can say the adversary in the middle captures the message and does replay attack. Then source repudiation, the source sent the message and later denies that he or she did not send the message. Destination receives the message, later says that it did not receive the message. So these are some of the issues that could arise in any message transmission across a network or while the data is in storage. So any security system that we are going to put in place has to satisfy these some requirements that could address the issues which we have discussed now. The encryption technique also can be used to perform the authentication. Both the symmetric and asymmetric encryption techniques can be used. Now let me discuss the symmetric encryption technique, how it can be used for the authentication purpose. So the message is encrypted using a symmetric key and the ciphertext is produced, and ciphertext is sent to the destination, and in the destination B, using the same symmetric key, it is decrypted and plain text is obtained. Here the sender and the receiver, sender A and the receiver B, both share this symmetric key and no other person knows this key, and hence this symmetric encryption technique is helpful in the process of sender authentication. So the sender is authenticated. If the decryption is successful, then it implies that only the sender has sent the message. Okay. So and also it provides the confidentiality since the ciphertext is transmitted across the network. For the purpose of integrity check, if needed, we can add hashing algorithm or MAC along with the encryption technique. Now let us see the public key encryption technique. So in the public key encryption technique, there are encryption and decryption technique. There are two keys, one is public and another one is private. So the sender A, let us say the sender A wants to send the message to sender B. So both, let us assume sender A has a key pair public and private, and receiver B also has a key pair public and private. Both the parties A and B, they keep their private keys secret with them. They don't reveal the secret key. However, the public key they share with other parties. So the A share its public key with B, and B share its public key with A. So you can see here, the A, when it is sending a message to B, it is encrypting the message with its private key, and this encryption is for source authentication. So this does not provide the confidentiality. Why? Because it is encrypted using the private key of the sender. So this ciphertext can be decrypted using the public key of the sender. The public key of the sender is open. It is revealed to everyone. Hence, anyone in the network, those who have the public key of the sender, can decrypt and see the message. So this encryption is basically used for the purpose of source authentication, to authenticate the source. So this ciphertext, when someone is able to decrypt successfully using the public key of the sender, here it is done, it shows that only the genuine sender has sent the message. The person who possesses the private key of this key pair has sent the message. It is confirmed. So it is used to confirm the source authentication. So if this public key is matching with this private key, it means the sender is a genuine person. Now this ciphertext here, you can see at the next level, it is encrypted using the public key of the receiver. B is the receiver. Why? This is done for the purpose of confidentiality. So now this, once again, this ciphertext again it is encrypted using the public key of the receiver. Now this ciphertext, when it is transmitted across the network, no one can decrypt and see the message without having the private key of the receiver. So private key of the receiver is secret with the receiver. No one can know that key. Hence, the adversary or the opponent, without having the private key of the receiver, they cannot get the plain text here. So this ciphertext is transmitted across the network. So when it reaches the destination, it is first decrypted using the private key of the receiver. So when it is decrypted using the private key of the receiver, again you get a ciphertext, and that ciphertext is decrypted using the public key of the sender, and now the plain text message is obtained. So using this technique, the source authentication is confirmed and also is implemented, and also the confidentiality also exists in this technique. Now message authentication code. So the message authentication code, it accepts message of variable size, and using a key, symmetric key, it produces the MAC value. So that MAC value is attached with the message and sent to the receiver. The receiver, using the same MAC algorithm and symmetric key, produces the MAC and verifies the MAC with the MAC sent by the sender. If they are matching, if the message is same, then the message is authentic and integrity is checked. If it is not matching, then the integrity of the message is compromised, and also the sender authentication also fails. So when you compare with the hashing technique in the lecture 1, here we get both the message authentication as well as the sender authentication, and also here a key is involved to produce the MAC value, and it is a symmetric key. So both the sender and the receiver, they have to share this key. So this is what given here. The output or the MAC value produced by the MAC algorithm is fixed size, like 512 bits or 256 bits, depending on the algorithm which is used inside the MAC, hashing algorithm used in the MAC. So a secret key is used, and also it is not reversible. So when MAC value is produced, from the MAC value, okay, it is not possible to get back the message. It is one way actually. So from message, like if you take encryption, so the message goes as the input into the encryption algorithm. The encryption algorithm produces a ciphertext. So from the ciphertext, we can again decrypt and produce a message. However, in the case of hashing and MAC techniques, from the MAC, it is not possible to go back to the message. So this is whatever I have explained now here, okay, is described here. Okay, and same concept already I have explained here. Same thing is explained using this diagram. Message, MAC function, it accepts a key and a message and produces a MAC value. It is attached with the message, and in the destination the message again, from the message again the MAC value is computed, and it is compared with the MAC value sent by the sender. Now let us discuss some points here. So now actually using the MAC technique, okay, there is no confidentiality for the message that is sent from the sender to the destination. You can see here the message is not encrypted. So someone can intercept these messages and can see the plain text. So in order to implement the confidentiality, okay, if needed, encryption can be used. So if encryption has to be used, once again you need another key for encryption purpose. So sometimes you can use the same key, or you can use different keys, one key for the MAC and another key for the encryption algorithm. Then MAC is not a digital signature and it does not provide the non-repudiation. So what is a digital signature? We will discuss in the next chapter. To explain in short, the message is hashed and the hashed value is encrypted using the private key of the sender to produce a digital signature, and this digital signature can be used for non-repudiation purpose. So we will discuss that in the chapter 3 in detail. However, the MAC technique, okay, cannot be used for the non-repudiation. So let us discuss some MAC properties. MAC basically is used to check the integrity, and it is used to authenticate the message as well as the sender. So the input is of variable length. It accepts a key, the functions accepts a variable length message, and it accepts a key as the input and produces a fixed size MAC value, or in another word we can say authenticator. And it is a one-way function, that is, from the MAC value it is not possible to get back the message, and also many to one function. So what it explains is, when we compute the MAC value for many messages, let us say we have millions of messages, and for millions of messages we are calculating the MAC value. Okay, there is a possibility that more than one message can produce the same MAC value. So that we call it as many to one function. However, please understand, a good efficient algorithm should produce less amount of collision. That is, it shouldn't give the same MAC value for more than one message. Okay, that is what given here. Finding these MAC values, I mean the collision, should be very difficult for a good and efficient algorithm. However, this possibility always exists, many to one function. Many to one means many messages, sometimes they can produce the same MAC value. Then requirements for the MAC. So a good MAC algorithm should have certain requirements to considered as a efficient algorithm. Knowing a message and MAC, it should be infeasible to find another message with the same MAC. So what it explains is that you have a message X. So for the message X, okay, you have a hash value, a MAC value, let's say M1. Okay, MAC 1 is the MAC value for the message X. Now another message, let us say Y, it shouldn't produce the same MAC value. Okay, so the algorithm should not allow that to happen. Okay, it should be a remote possibility. Okay, it should happen, it shouldn't happen frequently. So for any efficient and good algorithm, okay, knowing a message and MAC, it should be infeasible to find another message with the same MAC. MAC should be uniformly distributed. What it means, for example, when we toss a coin, okay, the probability of getting head and tail are even. Okay, if we toss a coin, okay, and say head or tail, so what is the probability of getting the head and even? They have equal chance. Okay, similarly, let us say we have set of MAC values. Okay, we have, for example, we have set of messages. For the set of messages, let us use some MAC function to produce MAC values. Okay, so the probability of getting a particular MAC value should be evenly distributed. That means a particular MAC value, whenever we compute, already I have told you, no, the MAC function is many to one. That means two messages, sometimes they can produce the same MAC value. So when we are computing the MAC value for set of messages, a certain MAC value should not be produced frequently. You get the point? The MAC value should be random in nature. It should be uniformly distributed. So whatever possible MAC values, okay, we can get should be even. It shouldn't be it should not be predictable in nature. It should be random in nature. So the MAC actually produces a fixed size output. Okay. So for the MAC function, the message of variable length goes as the input and it produces the fixed size MAC value. So let us say the MAC size is 512 bits. So the strength of the MAC value should be equally distributed across each and every bits. Okay, for example, if it is 512 bits, the strength of the MAC value should be equally distributed across 512 bits. Like for example, the strength of if someone is able to find a pattern in specific bits, okay, if the person is able to, if the adversary is able to find a pattern in specific number of bits, then it would compromise the security of the MAC function. So MAC should depend equally on all the bits of the messages. Okay, so it should not reveal a certain type of pattern in its MAC value distribution across its bit values. Now let us discuss data authentication algorithm. And this data authentication algorithm uses the DES encryption algorithm internally and CBC mode of chaining to calculate the data authentication code, or we can say it's MAC code. So the data of any arbitrary length is split into many blocks, D1, D2, okay, like that, Dn minus 1, Dn, and this is the last block. If needed to make the data into multiples of 64 bits, padding has to be done. Padding means like adding zeros and ones to make the data message into multiples of 64 bits as far as this algorithm is concerned. So D1 is the first block of data that would go as the input into the data encryption standard algorithm, and the key size used for the encryption is 56 bits and K is the key, and this is the ciphertext, and it is of size 64 bits. Let us say it is O1. Now this will be used in the next iteration of this algorithm. So the second block of the data and the O1 are XOR operation. So if you have any problem with XOR operation, you can Google and check what is the XOR operation. Okay. So the second block of data, okay, and the O1, okay, XOR, and the output what is obtained from the XOR operation will go as the input into the encryption algorithm, and the same key is used, and you would get the output O2. So like that the iteration goes on, and finally you get the output ON, and here the ON, okay, we can extract the data, that is the data authentication code we have to get from the ON, and the size can be between 16 bits to 64 bits. So, the data authentication code here, it should be greater than or equal to 16 bits or lesser than or equal to 64 bit. Okay. So, this is how here the message authentication code is computed, okay, using the data authentication algorithm. Now, let us cover the topic of HMAC, hash message authentication code. It is specified as the request for comment 2104. So, let me directly go to the HMAC structure and explain. For the HMAC function, the basic inputs are key and the message. So, key already we know this, we have discussed this here. The basic input for the MAC algorithm or key and message. Now, from the key, k plus k to the power plus is derived. This k to the power plus is derived from the key k. How it is derived? When the key is given, the key would be padded with zeros on the left, so that the number of bits would become b. So, b is nothing but block size. B is nothing but block size. So, for example, in the chapter 1, okay, we discussed the concept of SHA-512 algorithm. So, in that the message would be split into different blocks, n number of blocks, and each block would have a specific size. Example, SHA-512 algorithm, the block size is 1024. Okay, so that is the B block size. So, in the HMAC algorithm, you can see here some hash algorithm is used. If SHA-512 is used, then the block size is 1024 bit and the hash value is 512 bit, that is denoted by n. Okay. So, block B is the message block. If SHA-512 is used, then the B is 1024 bits and n is the output hash value, that is n bits. If SHA-512 is used, it is 512 bits. Okay. Now, for any MAC algorithm, already you know that the basic inputs are key and the message. From the key, k to the power plus is created by adding the zeros, so that the key size become b. Then a value called iPad and the values called iPad and OPAD are created, and this k to the power plus is used here. Okay, I shall explain, okay, after discussing the basic variables used in this algorithm. So, iPad basically, you know, it is a value 36 in hexadecimal represented as binary bit. Okay, this is the value 36 in binary format. Okay, so this iPad basically now it has only 8 bits. It should be it should have the size of the iPad should become b bits. B, for example, just now we discussed, if the SHA-512 algorithm is used in hashing, then the block size of the message is 1024 bits. Okay, so here it is only 8 bits given. Okay, how the 8 bits came? Okay, the value 36 in hexadecimal format is converted into binary format. So this 36 is represented in the binary format, and now this is just 8 bits, but we want this to be converted into B bits. The size should become B. Okay, how this can be done? Just by repeating this 8 bits, okay, many times, as many times as required, so that the number of bits become 1024 and the number of bits become B. Okay, if here the B divided by 8, okay, that many times, this value has to be repeated. Suppose if the B is 1024 divided by 8 will give you 128 times. So this value has to be repeated 128 times. So the number of bits will become B. Okay, so this is how iPad is calculated. Similarly, same logic for the OPAD, but the initial value here used is 5C in hexadecimal format. So the 5C in hexadecimal format is represented as binary value like this, and it is repeated B divided by 8 times. Already you know, if the B is 1024, then a number of times this value has to be repeated is 128 times. Okay, so this value will be repeated 128 times, so the number of bits becomes 1024. If the B is 512, if the block size is 512, then 64 times this value has to be repeated. Okay, so please recall what is k plus k to the power plus. Okay, it is nothing but the key value padded with zeros on the left, so the number of bits in the k to the power plus becomes B number of bits. B is the block size. So H is the hash function. Okay, IV is nothing but initialization vector. Okay, recall the lecture 1 please. In the hashing algorithm, initially initialization vector H0 is given as the input to the function f, hash function f. Okay, and the output from the hash function x, okay, is added with the initialization vector. Okay, arithmetic addition modulo 2 to the power 64. Okay, you can recall, go through the lecture 1. Okay, so this value is the initialization vector value. Then the message, the blocks, how many blocks of data, the data is split into, okay, many blocks. And K is the secret key. Now let us discuss the HMAC algorithm. So again recall, there are only two input, one is message and another one is key. So when the key is converted into K to the power plus, K plus, okay, and iPad is calculated. How iPad is calculated? Okay, you can recall this, and OPAD also calculated. Now the K plus and the iPad values each, okay, is of B bits. If the B is equal to 1024, then the K plus size is 1024 bit and iPad size is 1024 bit. Okay, now both are, okay, XORed and the output value is SI. Okay, just a minute. So k plus XOR IPAD, okay, it would give the SI value. Now this Y0, Y1, YL minus 1 is nothing but message. Okay, so here this shows the number of blocks. L is the number of block you have. Each block would have B bit size, is of B bit size. Okay, same logic here. This message, in SHA-512 algorithm is split into many messages, many blocks. Okay, and each block would have 1024 bit. Okay, so this is same logic here. The message is split into Y0, Y1, YL minus 1. Why it is YL minus 1? Because here it's starting from Y0. Each block would have the size of B bit. Now this SI value and the message value both are concatenated, they are combined, and this total value, combined value of SI and the message is multiples of B bits, is multiples of B bit block. Okay, because that is the essential requirement for any hashing algorithm, you understand. So now these blocks of messages along with SI, which are of multiples of B bits, goes as an input into hash function. So hash function can be SHA-512 or SHA-256, any hashing algorithm can be used. So these blocks of data goes as a input into the hash function, and also you can recall from the chapter 1, the hash function also has a input initialization vector, not a input, but it is internally generated by the hashing function. Externally the user need not give this IV value, but it would be generated internally by the hash function. Okay, so you can recall that here. So IV value of 512 bits according to SHA-512 algorithm. So hash function would produce the hash value, and the length of the hash value is of n bits. Okay, so hash of SI concatenated with M message. So this is a SI, okay, combined with message M, and SI combined with message M is hashed. So this is represented using this expression H, okay, hash of SI, okay, concatenated with message M. So now how the SI is obtained? SI is obtained by XORing the k to the power plus and IPAD. How k plus is obtained? K plus is obtained by padding zeros on the left, so the number of bit in the key becomes number of bits in the key becomes B. B is the block size, and IPAD, you know how it is obtained, and OPAD also you know how it is obtained. Now the hash value is n bits. Okay, now again this hash value has to be combined with S0. Let me explain what is the S0. Before that, this hash value has to be converted, the number of bits in the hash value should be adjusted according to the block size. So padding has to be done. So suppose here if it is SHA-512 algorithm, the hash value is of size 512 bit, but whereas when this 512 this hash value is given as an input into the next hashing function, some bits has to be padded so that the block size becomes 1024 bit B bits. Okay, so the hash value is padded, okay, and adjusted in such a manner that the number of bit becomes B. Now S0 is derived. How S0 is derived? Again, k to the power plus is XORed with OPAD value. You know how OPAD is obtained. Okay. Then this XOR of k plus OPAD is called S0. It is combined or concatenated with the h of si concatenation m. So this combined value is again hashed. Okay, then the initialization vector value, it is internally generated by the hashing function. And now finally what value we get here is the HMAC value. It is of n bit. Okay, if SHA-512 is used, it would be of size, okay, 512 bits. So this is the overall architecture of HMAC, hashed message authentication code. So here the hash function, we can fit any hash function into this. Okay, so this is what explained here, students. Whatever I explained is given here. Okay, this HMAC standard is specified in the RFC 2104. HMAC of message using a key K, you know, the expression is given this. The expression is nothing but this one. Okay, what is this happening? SI is calculated, SI is derived, then message, this is the message, both are hashed. Okay, they are hashed first. So this is what is happening here. Okay, iPad, okay, XOR K plus, this is SI. Okay, this one, or S1 we can say, or SI. Okay, then so that one is added with the message M. So this SI is added with the message M, and they are hashed together. They are hashed. Okay, then after that, parallelly what is happening, K plus is XORed with OPAD here, K plus is XORed with OPAD here. So please student, what is XOR? Please, it's very simple, XOR operation and all. So you can just refer the internet, what is XOR operation. Okay, these are basic things each and every student should be knowing when they deal with cryptography. Okay, so K plus XORed with OPAD, and S not is derived. So this is this K plus XORed with OPAD, and now it is combined with the previous hash value, and then again it is hashed, So this complete HMAC architecture is represented using the expression here. Okay, where K plus is the key padded out to block size. So when the key is given as the input, some bits are added in such a manner that the key size becomes of block size. OPAD and iPad, how they are derived? Okay, you know, just now we discussed that. Okay, then this is very important. We can fit any hashing function into the HMAC. So like MD5 or SHA-1, SHA-256 or 512, we can fit them here. Okay, so this is what I want to explain about the HMAC architecture. So the security of the HMAC is dependent on the hashing algorithm also, as far as the brute force is concerned. For example, when set of messages are given, you want to find the valid HMAC value, MAC value, then brute force attack can be used. And also birthday attack, you can check the chapter 1, that also can be used to compromise the security of the HMAC. Okay, so basically when we deal with the HMAC, in order to improve the strengthen the security, okay, choose the hash function based on speed, okay, and also based on security constraints. So we can use go for good algorithms such as SHA-512, etc. Now let us discuss the concept of authenticated encryption. Authenticated encryption is a term used to describe the encryption systems that simultaneously protect confidentiality and authenticity, that is the integrity of the data when the message is transmitted across a network. Many applications and protocols require both form of security. However, until recently the two services have been designed separately. So these are the four approaches of providing confidentiality and encryption for a message M. The first one is hash then encrypt. So here first compute the hash. Okay, you have the message. For the message, hash value is calculated, that is added with the message, and then hash along with the message is encrypted using a key. So this approach is called hash then encrypt. So here this approach provides the integrity as well as the integrity check as well as the confidentiality. The second approach is MAC then encrypt. So from the the word itself we can understand. First MAC value is computed. This is a message. Using the key 1, MAC value is computed. Then that MAC value is concatenated, attached with the message M. Message along with the MAC value is MAC computed using the key 2, K2. Let me repeat. First, the MAC value is calculated for the message M using the key K1, and then that MAC value is attached with the message M. Message M combined with the MAC value is encrypted using the key 2. So two different keys are used. This approach is taken by the SSL TLS protocols. The next one is encrypt then MAC. So here previously also two keys are used. So here what is happening is first encrypt the message to yield the ciphertext C. So C is equal to encryption of the message M using the key 2. So first encrypt the message to yield the ciphertext. So first obtain the ciphertext using the key 2, then obtain the MAC value for the ciphertext. So here the ciphertext, for the ciphertext C, using the K1 key, MAC value is computed. So encrypt then MAC. So from this you can understand, first you have to do the encryption and use the ciphertext to compute the MAC value. Then this approach is basically used in the IPsec protocol. The third one, encrypt then MAC. The fourth approach is encrypt and MAC. So here also two keys are used. Encrypt the message to yield the ciphertext C using the K2 key, then authenticate the plain text T with the MAC value. So the MAC value is calculated for the message M using the K1 key. So this approach is used in the SSH protocol. Okay, encrypt and MAC. Both in all the four approaches, encryption, decryption and verifications are a straightforward approach, but these approaches they have some vulnerabilities also. Now let us discuss the concept of counter with cipher block chaining message authentication code, CCM in short. NIST standard SP 800-38C for Wi-Fi. The standard for the Wi-Fi is this. This is based on the previously discussed approach, authenticated encryption approach, encrypt and MAC, the fourth approach. First encrypt, encrypt and also compute the MAC value, okay, using two different keys. So this is a variation of encrypt and MAC approach. This algorithm, the basic components are this AES algorithm, CTR mode of operation and CMAC authentication algorithm. So this, okay, so the basic are this encryption algorithm is AES and it uses the CTR mode of operation. Okay, so what is this CTR mode of operation? Let me explain this to you. This is a technique of doing encryption. So we have some encryption algorithm. Okay, for the encryption algorithm, some counter values are generated, like 1, counter 1 value, let us assume 1, counter 2 value, let us assume 2, counter n, counter 3 value, let us assume 3. So some counter values are generated and this counter value goes as an input into the encryption algorithm along with the key, okay, the key length, and the counter value depends on the type of encryption algorithm used, example AES, DES, etc. So the output from the encryption algorithm, the ciphertext, is XORed with the message block. So the message block, the basic message which has to be encrypted, doesn't go as an input into the encryption algorithm. Rather, the counter value and the key are taken as the input by the encryption algorithm and produces a ciphertext. And okay, the message is split into n number of blocks. Let's say each block is represented by P. P1 is first block, P2 is second block, and Pn is the last block. So the output from the encryption algorithm is XORed with the block of data, and what you get is the ciphertext C1. Okay. So this is how the operation takes place. Then the counter 2, okay, goes as the input, okay, to the encryption algorithm. Key is given and then it produces a cipher value, and that is XORed with the second block of data. Then it would give the ciphertext again. So this type of operation, encryption, is called CTR mode of operation. CTR mode of operation. Okay. So counter with cipher block chaining message authentication code, CCM. Okay, this technique, CCM technique, uses the CTR mode of operation, which I have explained here. This is how in the CTR mode of operation encryption is done and decryption is done. Clear now? Okay, now so this technique, for this technique CCM, AES encryption algorithm is used, advanced encryption standard, CTR mode of operation is used, and HMAC authentication algorithm is used. Okay, now let us see how this works. So we have some data message. Now this message is attached with the nonce value, some random values, okay, and then associated data. So this, what is this associated data? Basically it is like header files. When data is transmitted from one system to another, header files, protocol headers. So this is the message, this is associated data, this is a nonce value, some random value. So all these things are combined and it is split into blocks B1, okay. So like that it is split into many blocks and these basically each block of, for each block of data, the HMAC, so this blocks of data goes as an input into the HMAC algorithm, okay, and a key is given as the input into the HMAC, and this tag value or the MAC value is computed. This is the MAC value for this message. This is the MAC value, okay. So here as far as the CCM technique is concerned, same key is used. So in the image A shows the how MAC value is computed. In the B diagram shows how encryption is performed. So for both the MAC value computation and for the encryption, same key is used, okay. So now here for the encryption, the CTR mode of operation is used. As far as the CTR mode of operation is concerned, you know it needs counter values, counter 1 0, counter 1, counter 2, counter 3, like that. Is it clear to you? So the counter value, for example, it can either start from 0 or 1, okay. So using the the plain text is encrypted, plain text is converted into ciphertext using the counter CTR mode of encryption technique, and the counters used are from counter 1, okay, and until counter n, okay. Okay, so here basically the counter 0 is not used here. The counter starts from 1 to n, okay, and the key also goes as an input to the CTR mode of operation, and the ciphertext is calculated. You can see here to encrypt some data using the CTR mode of CTR technique, you need the counter values as well as you need the key, okay, you need the key. So this counter is generated, and let us say the counter values generated are from 0 to, okay, n minus 1, like that, okay. So here the counter 1, from counter 1 until counter n minus 1 is used for the encryption of the plain text, the message, okay, the main part of the message is encrypted. Now counter 0, please understand, the counter 0 is basically used to encrypt the tag. The tag is nothing but MAC value, okay. So this is the encryption of the message, plain text, this message, and this part basically is the encryption of the tag value or the MAC value. So CTR 0, that is counter 0, is used for the encryption of the MAC value, whereas the main message part, to encrypt the main message part, counter 1 until counter n minus 1 is used. So here this counter 0 using the counter 0, it is encrypted. Okay, so the output what you get actually, it is trimmed, shortened according to the length of the tag. So the length of the tag is nothing but t-len. Okay, so whatever output is obtained, that is obtained from the encryption algorithm, it is from that, okay, the most significant bits, okay, according to the length of the MAC value is chosen, and that value is XORed with the tag, again, and what you get is a ciphertext, and this block of ciphertext is for the tag value or MAC value. Okay, so this is how CCM operation functions. Let me recall. CCM operation is based on the encrypt and MAC approach of the authenticated encryption technique. It uses the AES encryption algorithm. It uses CTR mode of operation, and also it is based on CMAC authentication algorithm, and it uses single key for both encryption and MAC. You can see here. Okay, students, here A shows how the MAC value is calculated. Okay, then the B part shows how encryption is done. So the B part has divided it into two blocks. Actually, this is the main message. For that, using the CTR mode of operation from counter 1 until counter n-1, using that and the key, the encryption is done. And for calculating the ciphertext for the MAC value, okay, so basically it is done like this. Key is given as an input, okay, and counter 0 is used, and whatever output obtained, it is trimmed to the length of the tag value, that is XORed with the tag again, and what you get is a ciphertext. The last topic in this lecture is pseudo random number generation, PRNG, using hash functions and MACs. So the random number generation is very important concept in security. So basically in cryptography, these random values are used so that it is difficult for the adversary to predict certain pattern in order to compromise the security. So true random generation means, students, the true random number generation means obtaining the random values using naturally occurring events such as mouse clicks, keyboard strokes, etc. So using that seed values, we can generate a true random number. But now what we are discussing is called pseudo random number, which is achieved using the algorithms such as hash, encryption, MAC. Okay, the essential element of the PRNG are seed value. Seed value is nothing but some random value, okay, which we have to generate and which we have to give as an input into this PRNG function in order to obtain the random values. Okay, so in order to generate a random value, okay, you have to provide some sort of we have to provide some sort of nonce values, okay, which we call it as a seed. The seed must be known only as needed. Okay, only the known, I mean the people, those who are supposed to know the values, only they have to handle and know these values. So PRNG can be computed using encryption algorithm, hash function and MAC. Now let us see this how it is done using as function. Let us assume this V as the seed, okay, and repeatedly add the 1 to the seed V, okay, initialize this V and repeatedly add 1 to the V as much value as much required, then this V is hashed, and from that you just choose n bits of as a random value. Okay, it's a very simple explanation. Okay, so this is a seed value, this variable is initialized, and repeatedly adding the 1 with the seed variable, and that the seed is hashed to get the random value. So the security of this PRNG based on hash function depends on what kind of hash function is used. So next one is the PRNG using MAC. So MAC PRNG is the specification is given IEEE 802.11i, is used in the TLS security Wi-Fi. So you know HMAC involves key. Okay, so the final MAC value what is obtained, that would be, that serves as a random value. So with this I conclude this lecture. So in this lecture we have studied about the message authentication, the security requirements, then message authentication using encryption, then MAC, HMAC, and authenticated encryption approaches, then pseudo random number generation. So all these things we have discussed in this chapter. Thank you very much.